In a previous lecture, we looked at all the different uses of const. In this lecture, we're going to take a look at several different uses of static. We've previously talked about using static with a local variable so that the function containing that local variable is able to retain a memory of what happened the last time the function was called. As a reminder, here on slide 2, we have this not very random number generator, nvrand. When we call nvrand, seed is allocated on the stack as a local temporary variable initialized with 2. Then we do a computation involving some prime numbers and return the new calculated value of seed. Unfortunately, as soon as the function returns, seed is deallocated from the stack, and so the next time we call this same nvrand function, seed is going to get recreated, initialized with 2, and we'll end up getting the same random number back over and over again. So our solution to this problem is shown on slide 3. We prefixed static in front of the declaration of seed. Now seed is allocated in the static data area, and it exists whether we're currently executing this random number function or not. When we call rrbrand, the really bad random number generator, the first time, that is when seed in the static data area is initialized with 2, and later when we call this function again, that initialization part is ignored, and we simply have the value of seed as it had been computed the previous time this function was called. So the first time we call the function, seed is initialized with 2. Seed is recomputed involving these prime numbers in a linear congruential algorithm, and we return the updated value of seed. The next time we call this function, seed will contain whatever that previous updated value was, and we recompute seed and return a different random number. Now, we describe this as a bad random number generator because a linear congruential algorithm is cyclical, and if the random number that you get back is, let's say, 17, then you know exactly what the next random number is that you're going to get back from the formula used to compute the seed. For many applications, this is random enough, but it's not really very good. We also talked about global variables. A global variable is a variable defined outside of any function and is visible throughout the entire program, except for nested blocks of code, such as functions with parameters that have the same name as the global variable, or that have a local variable that's the same as the global variable. In those nested situations, the global variable will be hidden from view. You can only define a global variable one time. You can declare the global variable as many times as you wish using the keyword extern. And in fact, if you need to share access to a global variable between files, you must use the extern keyword in any file that's going to want to have access to that global variable. Here on slide 5, we've declared I as an int initialized with 42. I is a global variable here because it's defined outside of any function. And in order for I to be accessible in some other source code file, here we have file a.cpp on the left side, in that other file we have to use the declaration extern int I. The extern declaration tells the compiler, "Dear compiler, I promise that there is this global variable containing an int called I, but I'm not defining it here. It must be defined somewhere else. All right, so we have one and only one definition, which in this case happens to be in file b.cpp. We're permitted to have as many extern declarations as we wish, anywhere that we wish. So in file a.cpp, we're saying extern int I above main. We're also saying extern int I within main. That's fine. That's just declaring the same global variable as extern. And even in the file where we defined I as a global int, we're saying extern int I, and this is also fine. So you can have, thousands of extern int i's strewn around through your source code files, as long as you have exactly one int I definition in exactly one of the files involved in your program. The linker is responsible for making sure that the global variable I defined in one file is tied to all of the uses of I where I was declared extern in other files in your program. Now, where static comes into this conversation about global variables is if you have a quote global unquote variable declared static, that is, if you have a variable defined outside of any function, but you put the static keyword in front of that definition, then all of the code in that same source code file will have access to that variable, but other code in other files will not. Now, strstrip refers to these as file local variables. I like to refer to these things as module variables, thinking that in some sense a source code file is a module. And the idea here is that you have a variable that just needs to be shared among a certain set of functions, but not any other functions. So you can define all of those other functions and the static global variable that they need to share in one file to get yourself a file local or module variable that these functions can share. And here on slide 7, we have a brief example. Notice in file 2.cpp, we have an int I variable initialized with 42. This thing is declared static, which means that all of the functions in this file 2.cpp file have access to that int variable I, but other files outside of file 2.cpp cannot access that int variable I. Over here in file 1.cpp, where our main function is written, I could say extern int I, but that would turn out to be an error when the linker tried to gain access to this supposed global variable I. All right, because in file 2, the variable I is global, but only within this file itself. The name I is hidden from other outside files. All right, so return I has access to I. Mult I by 2 has access to I within file 2.cpp, but any code in any other files cannot gain access to this file local variable or module variable called I. All right, so those are the two uses of static that we have discussed before. That is, you can have a static local variable within a function so that that function can maintain some memory of what happened with that variable the last time the function was called. And you can have a static quote-unquote global variable in a file so that only the functions in that file can share access to that variable. And code in other files cannot gain access to that variable, even if they try by using extern. Now, just as you can create file local or module variables by defining a variable outside of any function but declaring it static, You can do the same kind of thing with top-level functions. That is, you can have static top-level functions which are only accessible to the code inside of one particular file, as opposed to being accessible to all of the code in your entire program. Alright, so you can think of these as being like file local functions or module functions. Now, you probably recall that when we developed our binary tree class, we had a whole bunch of top-level helper functions that did the low-level hard work of messing around with the nodes in our binary tree. Ideally, we would like users of our binary tree class to have to use the class interface functions, that is, the class member functions, when they create and interact with binary tree objects. And we would like to make it impossible for application developers or other programs to directly make use of these helper functions. We can do that, as illustrated here on slide 9, by putting the word static in front of the declaration and or definition of a helper function. Okay, so here we have a class member function, the put class member function, that displays the binary tree onto the screen. It does this by calling a helper function named putBinaryTree, passing in the top of the tree, that is a pointer to the topmost node of the tree, as the argument to the helper function. If we declare the helper function static, then the helper function can only be used by the functions within this source code file. In this case, this is our binarytree.cpp implementation code file for our binary tree class. Okay, so this is a very common technique for defining functions that can be accessed by other functions in the same file, but that cannot be accessed by other functions outside of this file in other parts of the program. A fourth thing that static is used for is to define static data members of a class. If you declare a data member in a class to be static, that means, as should not be a surprise, that that data member is stored in the static data area, and importantly, what this means is that that data member is going to exist even when there are no objects of the class currently existing in the program. The static data member is going to be accessible to any member functions and friends in the class, just like non-static data members are. Now, as a picky technical detail, it turns out that you have to define a static data member outside of any of the class member functions, which you typically do in the code file for the class. Okay, so such a static data member is often called a class variable because the data member applies to the class as a whole, as opposed to what are often called instance variables, which are the individual non-static data members that are contained within each object of the class. So let's take a look at this in the context of the employee class that we've been working with in previous lectures. Here's how we've been doing things, shown here on slide 11. We have our employee class. In the employee class, there is a data member ID, which is const. Each employee object has its own ID within it. Supposedly, these ID numbers should be unique for the different employee objects that we have in our program. But we don't have any way of enforcing that currently because our constructor for the employee object takes the employee ID number as the first argument, and consequently this class, this employee class, is relying on outside code, relying on the application code to provide a unique ID number for each employee object that gets created. And this is not a great design. Ideally, the employee class itself would control ID numbers for employees and ensure that each employee does in fact get a unique ID number. So we're showing on slide 12 the use of a static data member to help us do exactly this. Notice that on slide 12 we've revised our constructor for the employee class so that only the initial name and the initial rate are passed into the constructor for the employee. We've established a static int data member called nextID that is shared by all objects of the employee class, and that in fact will even exist if there are no objects of the employee class currently in our program. In the code file shown here on slide 13, this is a picky technical detail that's easy to forget, but when you have a data member declared static in your class, you have to provide a definition of that static data member in your code. That is, in the code file that implements the class. So here we have that nextID is a member of the employee class. It is an int, and its initial value is 1. So that means that when we compile this code, link it into a program, and run the program, as soon as the program starts running, there is going to be this nextID int variable in the static data area that's part of the employee class and that is already initialized with 1 even before any employee objects are created. Then notice how we've modified our constructor to make use of this nextID variable. Instead of initializing the ID data member for an employee object with an argument that's passed into the employee constructor, what we're doing is we're initializing the ID data member from the nextID static data member. And we're post-incrementing nextID after we've used nextID's original value as the value of the ID for the current employee object. Consequently, each time this constructor gets called, it's going to initialize the ID of the employee object that's currently being created to the next available ID, and it will then increment nextID so that the next time we create an employee, that employee will be guaranteed to have a unique ID. Here on slide 14 is a small application to illustrate how the nextID static data member works within our employee class. We've got a main function here, and when we compile and execute this code, because the nextID data member is static, it is stored in the static data area and initialized with 1 even before the main function is called. Then when the main function is called, we have an employee object Alex in here that we're constructing with Alex as the initial name and 57.25 as the initial rate. Now, in the constructor, as we saw here on slide 13, the ID for Alex is going to be initialized with 1, that is the initial value of nextID, and after Alex's ID has been initialized to 1, nextID will be post-incremented to become 2. Alex's name data member is going to be initialized with the string Alex, and Alex's rate data member is going to be initialized with 57.25. Now we go on to creating this employee object Bob. Again, in the instructor, the ID for this object that we're constructing, Bob, is going to be initialized with 2, the current value of nextID, and then the current value of nextID will be post-incremented to become 3. Bob's name will be initialized with the string Bob. Bob's rate will be initialized with 63.10. So we now have 2 employee objects, Alex with an ID of 1 and Bob with an ID of 2. And the next available ID is going to be 3. Carl is a manager. A manager is a kind of employee. For the manager constructor, we have made a revision so that we do not specify an initial ID number. All we specify is the name, rate, job title, and budget. So the manager constructor, which we're not showing, we'll first invoke the employee base class constructor, passing down Carl and 66.75. Carl's ID will be initialized with 3, after which next ID is incremented to 4. Carl's name will be the string Carl. Carl's rate will be 66.75. At that point, the base class employee constructor is finished, and so we complete the initialization of the manager part. Title is initialized with boss, and budget, since we've specified a 0 value, as I recall, is initialized with $500,000. Okay, so we now have 2 employee objects, Alex and Bob, and a manager object, which is a kind of employee, Carl, whose ID numbers are 1, 2, and 3, respectively. When we run the program, the output is shown on slide 15. Alex.print will invoke the employee print function, printing out employee number 1, name Alex, rate 57.25. Bob.print also invokes the employee print function, employee number 2, name Bob, rate 63.1. Carl.print will invoke the manager print function because we overrode the print function in the manager class. So we get out manager information, and contained within that manager information is the employee information, employee number 3, name Carl, rate 66.75, followed by the title and the budget for Carl. Let's take another look at the application shown on slide 14, but this time with some diagrams showing what's going on in memory while this application is running. So we run the program, and the very first thing that happens, as shown here on the right-hand slide, is that the employee : next ID static data member is created in the static data area and initialized with 1. And in fact, that happens even before main gets called. Now, when main gets called, and the first thing that happens in main is that we create this local temporary employee variable named Alex on the stack, here's what we get. Alex is created in the stack. The 4 data members that Alex has access to are next ID, which is actually not locally contained within Alex. That is actually the static data member next ID, but the member functions for the employee class are able to use that member name next ID. ID is a const int initialized with 1, which was the original value of the employee : next ID static data member. Name is initialized with the string Alex. Rate is initialized with the double 57.25. Notice that after Alex's ID was initialized to 1, employee : next ID was incremented to 2. The second thing that happens in main is that Bob is created. The object Bob, with its data members, is created on the stack. Next ID is not within the object Bob, but that name next ID for the static data member is available for member functions to use for Bob. The const int ID is initialized with 2, and then notice that employee : next ID is incremented to 3. Name is initialized to Bob, rate is initialized to 63.1. Then the third thing that happens is that the manager Carl is created. Carl is a kind of employee. Carl contains within itself an employee and also has additional member functions and data members at the manager level. Notice that using Carl we can access both the manager print function, which is our override. If we wish, we can also access the underlying base class print function by saying employee : print if we want to. Next ID is available for use by the member functions operating on Carl. Next ID simply is the static data member next ID, and ID for Carl is initialized with 3, And then employee : next ID is incremented to 4. Name is initialized to Carl, rate is initialized to 66.75, and once the base class constructor has finished its work, we continue with the remainder of the derived class constructor for the manager. We initialize title with boss and budget with 500,000. Then in the rest of main, we invoke print on each one of these things, and at that point the program is over, and all of these local objects, Alex, Bob, and Carl, are eliminated from the stack, and the static data object, employee : next ID, is also eliminated from memory, and the program is done. Our final use of the keyword static here in Lecture 6 is for static member functions of a class. A static member function can access and modify any static data members that are defined for that class, and in fact this is going to be true even when no objects of that class currently exist. So here on slide 17 we have an example of a static member function, getNextID, whose job is to return the value of the nextID static member variable. Even if there are no employees currently existing in the application, that is, no employee objects currently existing in the application, we can nevertheless use getNextID to find out what the next ID will be if we create an employee object. Static member functions are restricted from accessing non-static members. For example, an employee object has an ID, also has a name and a rate. But recall that a static member function can be used even if no objects exist. Therefore, it would not make sense for this static member function, getNextID, to be able to access the ID or the name or the rate of the current employee, because there is no current employee. There may not be any employees currently existing in the program at the time that we call this getNextID function. Okay, so static member functions can interact with static data members. They cannot interact with non-static members. Here on slide 18, we have an example program making use of our modified employee class that has this static member function named getNextID. In this program on slide 18, when we run the program and main is called, as we know, that static int data member nextID is allocated in the static data area and initialized with 1 even before main is called. So when main is called, even though we don't have any individual employee objects existing at this point, I can invoke this static member function, getNextID, for the employee class by using the notation employee : getNextID. Okay, I don't need there to be a current employee object in order to invoke this getNextID function. And at this point, because no employees have been created yet, employee : getNextID will return to me a 1. 1 is the next ID number that will be assigned when we create an employee object. Okay, so let me show the output on slide 19. The first line of output says, next unique employee ID is 1. Then in main, we do create an employee object named Alex. Alex's ID is initialized with 1, and then the next ID static data member is post-incremented to 2. When I print Alex, I'll see that Alex is employee number 1, name Alex, rate 57.25. And then, in this final cout statement, if I call getNextID, the value I'll get back will be 2, because 2 will be the value of the ID data member the next time I create an employee object. In fact, in this program, I'm not doing anything further. The program just ends at this point. In this example, notice that I did have an employee object, Alex, currently existing. So I am allowed to say alex.getNextID as an alternative to saying employee : get next ID. All right. So if you do have a current object like Alex sitting around, you can invoke a static member function on that current object, even though the static member function is not allowed to access any of the current object's non-static members. Okay, so that's our conclusion here for Lecture 6. We've reviewed 2 uses of static that we knew about before and introduced 3 more. We already knew about the idea of using a static local variable within a function to maintain some memory of what happened the last time that function was called. We already knew about using a static global variable within a file to create what Strustrup calls a file local variable, or what I like to call a module variable. We introduced the idea of declaring a function static within a file. In effect, that creates a module function that can only be used by other functions within that same file. And then we introduced the idea of static data members that are available to a class as a whole, and static member functions that can be used to interact with a class's static data members. And that's that.